Swayam Prabha. Digital India. Educated India.
Hello and welcome to lecture number 27 of this lecture series on jet aircraft propulsion. So, in this lecture series we have been discussing about the different components that constitute a jet aircraft engine. We have also discussed initially about some of the cycles that constitute or based on which jet aircraft engines operate. We have discussed about both the ideal cycles as well as the real cycles. We have also discussed in detail about how we can take into account the performance of different components which constitute a jet engine. Of course, during the time when we are discussing about the cycles, we assumed that these components are black boxes, in the sense that we were not really concerned about what was happening within these different components. We were just calculating efficiencies and pressure losses as the flow passes through these components. Then subsequently, we have started a discussion on individual components of the jet engines. We have already discussed about the compressors and the turbines. We have discussed about axial flow compressors and centrifugal compressors. We also discussed about axial and radial turbines, and subsequently on combustion chambers. Now, we are going to discuss about a few other components which constitute the jet engine. One of the important components that will constitute any jet engine is an air intake. So, in today's lecture, we are going to start some discussion on air intakes. We will have a preliminary discussion on the different types of air intakes that are used in different types of engines. And in the next lecture, which will be the next lecture, that is lecture 28, we shall discuss the performance parameters which are associated with these air intakes. So, today we will discuss about different types of air intakes used for civil aircraft as well as for military aircraft, and as we will see very soon that the air intakes can be quite different depending upon what type of engine it is to be used for. And in civil aircraft, the air intakes are usually simpler in terms of their configuration and design and geometry, whereas as the engine becomes more complicated, in the sense that if it is used for a military aircraft, a combat aircraft engine would need an air intake which is little more complicated than what is used in a normal civil aircraft engine. And so, we will see some of these geometries and different types of air intakes which are used in different applications. And then subsequently, we will also discuss about how we can assess the performance of air intakes and what are the performance penalties associated with the flow through an air intake, especially when it comes to a supersonic intake. There are different components of losses like shock losses besides the viscous flow losses itself. So, some of these performance related issues we shall take up for discussion in the next class. Today's class, we will just have an overview of different types of air intakes and how we can classify air intakes depending upon their application itself. So, today's lecture will be primarily discussion on intakes for transport as well as for military applications. Now, air intakes are probably, well, in fact, they are the first component that constitute an aircraft engine as it is. So, aircraft engines will always begin with an air intake. Of course, the engine manufacturer normally does not make the air intake itself. It is usually something which the airframe manufacturer would be responsible for, but of course, that will require that the engine manufacturer and the airframe manufacturer coordinate in the design process of the air intake. Now, this word intake is something which is usually used in the United Kingdom and in the United States it's usually referred to as inlet. They both mean the same, just that they are referred to in different ways in different countries. So, intakes is something used in the UK, and we are going to follow that in today's lecture as well. So, as I mentioned, intake manufacturing is something which is normally taken up by the airframe manufacturer. The engine manufacturer just supplies the engine, but of course, since the air intakes are an integral component of the engine as a whole, the design and development of intake would require coordination between the engine manufacturer and the airframe manufacturer. And so, the type of intake to be used for a particular application is very much dependent or is a strong function of the application itself. Like if an engine is to be used in a civil aircraft as compared to what is used in a military aircraft, the type of air intakes would be entirely different. And it is also possible that an aircraft can have multiple intakes, which is something you might have observed, that most of the transport aircraft would have multiple engines and each engine has its own intake. In a military aircraft, on the other hand, the engine is not something that you can visually see from outside. It is usually concealed within the fuselage. And there are certain types of aircraft where you have multiple inlets which are feeding into the same engine. There is one engine which is fed by multiple intakes, or you may have multiple engines which are individually fed by multiple intakes and so on. So, depending upon the type of application, you might have different types of intakes which are used in different applications. Now, what is the purpose of an air intake? The basic function of an air intake is that it is a medium, or it's a duct which basically connects the engine to the free stream in some way or the other. An aircraft engine, as we know, requires, it's an air breathing engine, so it requires air for its operation, and this air is supplied to the engine through the air intake. So, air intake is basically a device which delivers the necessary quantity of air to the engine, and that is not all about it. It is also required to supply this amount of air in a uniform manner, in the sense that air intake also needs to provide quantity of air to the engine. At the same time, it also has to ensure that the quality of air which enters the engine in terms of the flow uniformity is good. That is, air intake has to satisfy these two criteria, and it also needs to ensure that this much amount of mass flow, the required mass flow for the engine, is supplied under all the operating conditions. So, an aircraft engine will operate under very extreme conditions, like from takeoff, where it is at very low altitude and density is very high, to its cruise altitude, which is at an altitude typically around 11 kilometers or even higher than that, where the density is very low. So, under these extreme operating conditions, the air intake should still ensure that the amount of mass flow that is required for the engine operation, so that the engine can generate the requisite thrust, is provided at all times. And that makes design of air intakes quite a challenging task, especially for a military aircraft, where the range of operation is even more, especially if it is a combat aircraft, where it has to undergo very severe maneuvers and operate and sometimes even operate in supersonic Mach numbers, if it is a supersonic aircraft. So, under these conditions, for example, a supersonic intake has to not only operate in subsonic flow, it also has to operate in supersonic mode. So, design of such intakes can be quite challenging, whereas a civil aircraft, on the other hand, the operation is fairly limited, in the sense that we know it is going to take off, climb and reach a certain altitude, and eventually it would land back to the sea level altitude or so. So, the range of operation or the flight regime is quite fixed there, unlike a military aircraft, where it could operate under much more adverse conditions, which makes the design of supersonic intake or even a military intake a little more complicated than a normal civil aircraft intake. And so, we will see some of these designs of different types of intakes which have been used and which are currently in use in many of the aircraft during the course of today's lecture. So, air intakes will of course, the primary function as I mentioned is to capture free stream air, and in some cases also change the direction, which I will explain shortly, that in some cases the intakes are curved and because the engine is located at a different axial location, and therefore, it has to turn the flow, change the direction and then supply that to the engine. But this must be done with as little flow distortion or non-uniformity as possible. We will quantify flow distortion in the next class, how we can measure and put a number to flow distortion in the next class. And intakes also, because intakes are located out of the fuselage in the case of transport aircraft, and they are housed within what is known as a nacelle. The engine is located within a nacelle, and so the intake outer surface must also not result in excessive external drag, which again a point which I will explain shortly. And the most important aspect is that intake must ensure proper operation, or it must supply the required mass flow rate over the entire flight regime. And in some of the modern aircraft engines intakes, they also have noise absorbing materials to shield the engine noise from reaching the fuselage, and especially in a transport aircraft, some of the nacelle that houses the engine, and that is also where the intake is molded, contains noise absorbing materials which can partially shield the engine noise from reaching the fuselage, from reaching the cabin. And so, that is another function. Of course, that is not really a function of the intake as such, but it is part of the nacelle which houses the engine, and it also forms a part of the intake. So, I mentioned that the basic function of an intake is to direct air, or it is supposed to capture air from free stream and deliver that air to the engine depending upon the requirements of the engine. That is, as the pilot changes the throttle, the engine would be generating different thrust depending upon the throttle setting. So, depending upon how the engine requires or what throttle setting it is to be operating under, the intake is required to provide that much amount of mass flow rate to the engine, which means that if an aircraft engine has a lot of variation in its operation, like a compact aircraft, a normal intake which has fixed geometry may not really suffice. You may require that the intake geometry also needs to be variable, but most of the civil aircraft engines have geometries which are fixed, intake geometries which are fixed and do not change, unless it is of course under special circumstances, like in a high bypass turbofan, there could be an intake duct which goes into the bypass duct and so on, but that is many of the aircraft usually operate with fixed air intake geometry. But in military aircraft, on the other hand, or supersonic intake for example, would usually have a variable geometry intake to ensure that this intake can operate safely under subsonic conditions as well as under supersonic conditions, and so that will necessitate that the intake has certain variable geometric features incorporated in its design. So, I will show you some typical examples of air intake geometries which have been used and which are currently used in some of the civil as well as military aircraft engines. So, what I have here is a typical military aircraft, fighter aircraft here, and in this configuration that I have shown, it is an aircraft which has two engines. So, these are the two engines that you can see, and so immediately you can see that this configuration is very different from a civil aircraft or a transport aircraft, where the engines are usually exposed and you would see the engines beneath the wings, usually mounted beneath the wings. Military aircraft, that is or a compact aircraft, that is not the case. Engines are usually mounted within the fuselage. So, in this particular configuration, we have two engines. We also have two individual intakes or ducts which supply the air to the engines. In this case, you can clearly see that the engine is located far downstream towards the tail of the aircraft, which is how it is in most of the military aircraft, and the intake is supplying air from the sides of the fuselage in this particular configuration, and it is delivering that air to the engine. So, you can see that the intake duct is a curved duct in this case, and this curvature also leads to additional complexities which we will discuss in the next class. And so, this is one configuration of an engine wherein the intake, there are two intakes on either side of the fuselage and delivering mass flow rate to the two respective engines. There could also be configurations where there is only one engine, in which case these two intakes would merge and form a single duct before it enters into the engine. Now, this is another configuration of again a military aircraft engine, wherein the intakes are located in a different location as compared to what it was in the previous slide. In this previous case, you can see that the intakes are located on the sides and the engine is mounted towards the tail of the aircraft. In this case, also the engines are located towards the tail, but it is mounted on the underneath the aircraft fuselage, and the intakes are in this case not curved. So, the advantage of this intake that this intake has is that it does not require any curvature as compared to the previous one. There is a straight intake which delivers the required air to the two engines. You can also see that the intakes can have different cross sectional areas. So, in this previous case, the cross sectional area at the inlet was a donut, semi donut kind of shape here, whereas in this case it is a rectangular entry intake geometry at the inlet. But whatever be the inlet geometry at the engine face, at the compressor inlet, the geometry has to be transitioned into a circular geometry, because the compressor requires a circular duct, and therefore, the inlet geometry is eventually converted to a circular geometry before it enters the engine face. So, depending upon the application, let us say I mentioned that you could also have an application where there is only a single engine, which is what is the case here. There is a single engine and you have two ducts from either sides of the fuselage. These are the two ducts from the sides of the fuselage, which eventually merge before the duct joins the engine. So, these types of intakes are also referred to as Y-shaped intakes, because there are two ducts which merge and form a single intake. The first example I showed here are wherein you have a single duct feeding into a single engine, are sometimes referred to as S-shaped intakes because of its similarity to the letter S. So, these are usually referred to as S-shaped intakes, these are straight intakes, and these are usually referred to as Y-shaped or bifurcated intakes. Now, these are intakes which are probably quite different from what you would have normally seen in a civil aircraft. In a civil aircraft, the intakes are much more simpler and they are very short intakes, and we will see some examples of civil intakes also a little later. And if you notice in when you are probably boarding an aircraft the next time, you can notice that the engine is quite visible as you at least the fan, which is the first component that you would see of the engine, is quite visible as you see from the engine from the front. So, the duct which is just ahead of the fan or the compressor is the air intake, and which is quite unlike a military aircraft, that you would rarely see an engine face when you look at the aircraft from the front, and that is intentional, and I will probably explain some of those details either in today's class or the next. So, in military aircraft, it is the engine face is intentionally kept shielded from line of sight for this reasons that it has to have a lower radar cross section, that is a compressor phase or an engine phase. If it is exposed, the radar cross section of the engine could be quite high, because it will reflect the radar the incoming radar signals in it will be reflected in different directions, increasing the radar cross section. So, shielding the engine is one of the objectives of a military aircraft. which is not there for a civil aircraft or a transport aircraft, which is why the engines, it does not matter if the engines are really exposed. Plus the fact that in transport aircraft one would normally use a large bypass turbofan, and therefore it definitely needs that kind of mass flow, which is not possible if the engine were to be shielded. And there are of course other lot of other reasons why you cannot have an engine within the fuselage for a transport aircraft. Now, some of the modern military aircraft engines, if you were to try and look at some of the geometries associated with modern combat aircraft, the engines are very well shielded within the fuselage, and it is the duct that you would be able to see, which is basically the air intake which delivers the required mass flow rate. Now, in an attempt to increase or reduce the radar cross section even further, some of the next generation military aircraft would most likely have intakes which are much more complicated than what the current generation aircraft would have, and these are primarily meant to reduce the radar cross section even further, which would require that the air intake has a very complex geometry, and often these geometries are known as serpentine ducts or serpentine intakes. So, one such example is shown here in this schematic that I have shown, probably what we would see a few years from now in the next generation military aircraft, where the engine is of course very well shielded within the fuselage, and to reduce the radar cross section and prevent any line of sight to the engine, one needs to have an air intake which probably has a very high curvature as compared to what I had shown earlier for the Y duct or the S duct. So, these are known as serpentine intakes, and because of the very shape they have, and it is naturally expected that such intakes will suffer heavily from flow non-uniformities by the time the flow reaches the engine. So, currently there are a lot of research studies going on in trying to analyze this kind of geometries and try to improve these the flow through these ducts, so that the engine phase receives a fairly uniform inflow. So, what I have shown now, have been showing all these pictures are with reference to military aircraft, and I am assuming that you have already seen some civil aircraft intakes. I will also show you some pictures of civil aircraft intakes, but the very fact is that the intakes of normal transport aircraft are much more simpler as compared to supersonic or combat aircraft intake. So, intakes that are used in transport aircraft normally do not have such curvatures like in the S-shaped or Y-shaped or the serpentine ducts. They are usually straight and axisymmetric and circular. That means there is no change of cross sectional area from the inlet from the entry of the inlet to the compressor phase, and which is unlike a military aircraft, where normally there would be a change of cross sectional area and the geometry itself. It could be rectangular or donut shape at the entry, eventually becoming circular at the compressor phase. So, some of the differences between military and civil aircraft intakes are primarily because of the nature of operation of these engines themselves, and if, for example, a subsonic intake would also be different from a supersonic intake, and that is also something we will discuss a little later. And even in a civil aircraft, the other form of civil aircraft would be the turboprop. Intakes of turboprops are a little more complicated than the normal turbofan intakes. So, since most of the transport, in fact all the transport aircraft or civil aircraft that we know as of today which are operational are subsonic, the intakes of most of these aircraft are very similar in terms of their geometry, and they all usually consist of smooth continuous curves, which is unlike supersonic intake, where you could have sharp edges because of the fact that supersonic intakes decelerate the supersonic flow to subsonic through shocks, and that is created using certain sharp edges in the intake. And in subsonic intakes usually have a thick leading edge, which is known as the lip of the intake, which is obviously not something that is feasible to be used in supersonic flow, because thick leading edge can lead to the presence of a strong oblique shock or a bow shock at the ahead of the intake, which is not something that would be beneficial for the engine itself. So, subsonic aircraft intakes will obviously have a thick leading edge, and in the case of turboprops, the intakes can be slightly more complicated, because there is a propeller and also a gearbox ahead of the compressor, and therefore, that makes the geometry slightly more complicated. So, the difference between the intakes used for civil aircraft and a military aircraft would be clear from this slide here. So, this shows a typical transport aircraft, and so these are the intakes that you can see here. What you see at the center is the hub of the fan, and so this part of the intake is of the engine is basically the intake of this particular aircraft. And what you see here is the lip of the intake, which is a very thick leading edge of the intake, and the entire engine is housed within what is known as a nacelle. So, this is known as the nacelle of the engine, which that basically the core engine is mounted within the nacelle, and intakes form one part or the initial part of the nacelle itself. So, this is the intake of civil or a transport aircraft. On the other hand, this is a typical intake of a combat aircraft, and we can see that it is rectangular. There are two of them on either sides, and the engine is mounted inside the fuselage. So, you cannot really see the engine besides the nozzle. So, probably you would be able to see the nozzle of the military engine, but not the core engine as such. And so, the difference between this engine and this intake and the military intake is quite visible here. And so, in a transport aircraft, the intakes are much shorter, and the geometry, the cross sectional changes are also quite simpler as compared to a military aircraft, where there could be drastic change in cross sectional geometry itself. In this case, for example, ultimately it has to become circular. So, this rectangular geometry has to be slowly transitioned and made circular by the time it reaches the engine phase. So, so because of these differences between the intakes used in subsonic flow, that is subsonic intakes, and supersonic intakes, we will have a detailed discussion on subsonic intakes and also on supersonic intakes. So, today we will just take a look at what are the different types of subsonic intakes that are possible, and what are the different types of supersonic intakes that are in existence. So, subsonic intakes are, as I mentioned, usually axisymmetric, and so the most common type of subsonic intake that are used are known as pitot type of intakes. Pitot intakes are the most common types of subsonic. They are also of course used in supersonic flow, but they are very rare, but commonly used in subsonic flows. So, pitot intakes are the simplest form of air intakes possible, and they are axisymmetric, usually axisymmetric in nature. And again, there are different types of pitot intakes which we shall take a look at. So, most of these pitot intakes, or those which are used for subsonic flows, have fixed geometry. So, they do not really have any provision for varying the intake geometry while in operation. So, fixed geometry intakes, and except in some cases like in certain types of high bypass turbofans, where they have what are known as blow-in doors, which are used during certain modes of operation of the engine, but normally intakes are fixed geometry. And so, in the case of subsonic intakes, which are, let us say, used in turbofans, which requires certain amount of variability incorporated in them. This variation is required especially when the aircraft is taking off, when it requires the maximum thrust, which means it also requires large amounts of mass flow rate as compared to when the aircraft is cruising, when the thrust requirement is not that high. So, under certain circumstances, the engine might require additional mass flow, and that is when the intakes may have a blow-in door, where it supplies a little amount of additional mass flow to the bypass duct, and that may lead to that could provide additional amount of mass flow rate for the engine to generate additional thrust required during takeoff. But except under these circumstances, the intakes usually have fixed geometries. So, in the case of intakes, most of the subsonic intakes, as I mentioned, have fixed geometries, except in certain cases where we may use blow-in doors used in high bypass turbofan engines, which basically are meant to deliver additional mass flow rate to the air engine during takeoff and climb. And so, a typical pitot intake, as I mentioned, is usually axisymmetric because of the intake which I had shown for the transport aircraft, that is an axisymmetric pitot intake. In a pitot intake, geometry basically consists of the nacelle itself. Nacelle forms, intake forms one part of the nacelle itself, and within the nacelle is the engine. So, this part of the what is there beneath this nacelle is the engine, and what you see here is the hub of the compressor or the fan. So, the flow through this intake will constitute two parts. One is the external flow and the other part is the internal flow. That is, there is one part of the flow which gets split because of the presence of the intake itself. One part of the flow moves above the intake on the nacelle, that is the external flow surface. Other part of the flow goes into the engine itself, that is the internal flow. So, a typical subsonic diffuser is required to ensure that it not only produces or delivers uniform flow at the engine phase, it also is required to minimize external flow drag. So, because of the presence of flow through this surface, there is also a certain amount of drag penalty because of this. So, the intake designer, the nacelle designer has also supposed to ensure that the external drag is minimized under off design operating conditions. So, the leading edge of this nacelle, which is basically the beginning of the intake, is known as the lip of the intake, and then there could be which something we will discuss in the next class, that there are different areas of this where there could be flow problems. One is of course the external flow, which I mentioned that we should try to minimize the drag associated with the external flow, and under certain operating conditions there could also be flow separation external to the intake itself. Besides that, there could be flow related problems on the intake surface or on the hub surface. So, it could be either on this surface or on this surface or external to the intake, and all these three are basically a result of the intake operation under various operating conditions. So, a pitot intake is probably the simplest form of the subsonic intake, and there are the main reason why it is very commonly used is that the total pressure losses across a pitot intake is very less as compared to some of the other types of intakes which are existed. So, pitot intakes usually have very low, when operating in subsonic flows, have very low total pressure losses, which is a big advantage because total pressure loss in the intake can eventually lead to loss of thrust. So, total pressure loss is something that one would like to minimize, and that is something which is inherently present in pitot type of intakes, and so that is one main advantage. But the main advantage associated with the pitot intake is that it makes the best use of the ram effect due to forward motion as compared to many other types of intakes which are existent. So, pitot intakes are able to benefit from the fact that because of their very geometry, they are able to make the best use of the ram effect. As the engine moves forward, there is a ram effect for the incoming air. So, pitot intakes are able to make the best use of that with minimal pressure loss, and that is probably the most important advantage, besides the fact that it is much simpler in geometry as compared to other types of intakes. So, we will discuss in some detail about what are the different types of pitot intakes that are existent and what are their characteristic features of these different types of pitot intakes. So, as I mentioned, pitot intakes are commonly used because they can use the ram effect due to the forward motion, and they suffer minimum loss in ram pressure, especially in changes in when the engine is operating under different altitude conditions. But of course, these intakes, like the one which I had shown earlier, are meant primarily for subsonic operation, and because for an efficient operation of these intakes, it requires that the leading edge is smooth and it constitutes a certain curvature, which is not something that would be desirable for a supersonic flow, which is why these types of intakes are used primarily in subsonic flows. So, there are different types of pitot intakes. There are basically three types or which are commonly used. The probably the most common type of pitot intakes are known as podded intakes, which is normally used in transport aircraft, like the one which the picture I had shown earlier for a transport aircraft. That is a podded intake. Then we have integrated intakes and flush intakes. And podded intakes are usually used in transport aircraft, both civil as well as military. Even in civil, even in military aircraft, there are certain types of military aircraft which are used for transport of military equipment, and so those type of engines are normally the ones which would use a podded intake. And because the thrust requirement in such engines, you would not really want to operate at supersonic speeds. Subsonic speed with a high bypass turbofan is probably the ideal engine for such aircraft, and so for such an aircraft, a podded intake, which is a pitot type of intake, is the best solution for these intakes. Other type of intakes are known as integrated intakes. Integrated intakes are those which form part of, that is, they divert air from the fuselage into the engine, which is located probably within the fuselage itself, and something which would be used in some of the military aircraft, the combat aircraft. And the third type of pitot intake are known as submerged intakes, and these are used normally in missiles, especially if the missile is to be launched from a canister. Then the geometric advantages of submerged intakes are huge. So, submerged intakes may be used in missile type of applications. So, these three type of intakes are the most commonly used types of pitot intake. So, let us take a look at what these three intakes look like. So, the first one that is shown here is a podded intake, the one which is used in most of the civil aircraft and some of the military transport aircraft. And podded intake, as you can see, consists of a nacelle within which the engine is housed, and there is a thick leading edge, and this is the lip of the intake, and this is where the engine begins. So, this engine is housed within the nacelle, and you can see that this is an axisymmetric type of an intake. The other type of an intake, pitot intake, is the integrated intake. So, this is shown here. This is an integrated intake wherein the engine is mounted here, and it is not in the same axis as where the intake is beginning, which is why it is called an integrated intake, because it part of the intake, the engine is partly within the fuselage itself, and so the intake has to divert flow from the sides of the fuselage into the engine through a ducting. So, integrated intakes would normally require a duct, and so there are associated problems, like I mentioned. This is a typical S-shaped duct, and there could be issues with flow separation and flow non-uniformity at the engine face because of their very geometry. And the third type of pitot intake are known as the flush intake or the submerged intake, wherein the engine is well within the fuselage itself, and you would not want any part of the intake to be protruding out of the fuselage surface. And these are these are the intake types which are used commonly in missiles. So, as you can see from the side view, you do not see any protrusion from the fuselage, which is not the case in either of these cases, where either here or in this case the intake is very much visible. And so, in the advantage of main advantage of this type of an intake is that if the missile, for example, is launched from a canister, then it is necessary that there is nothing else nothing else is protruding out of the fuselage itself. Flush intakes or submerged intakes can ensure that this is possible, but of course there are performance penalties associated with this because of the very fact that the flow has to curve substantially or has to take a substantial curve before entering the engine. The performance of these intakes are usually very poor as compared to the podded intake or even compared to the integrated intake, and therefore that's the reason why they are used only under certain special circumstances, especially for missile applications and so on. Now, in podded intakes, the frictional losses, as I mentioned, are not very significant as compared to some of the other types of intakes. The performance of these intakes are subject to the flow behavior internal as well as external to the intake itself. So, there could be possibilities of flow separation not only within the intake, but also from the nacelle and leading to external drag, increase in external drag. But leaving that aside, the performance of podded intakes are usually better and frictional losses are minimal, but of course these are meant purely for subsonic flows, and as the engine, if the engine were to operate in supersonic flows, these intakes are not going to perform efficiently at all. And therefore, in the case of podded intakes, the presence of separation of course will affect the performance of all types of intakes, but if there is a separation within the surface of the podded intake, then it will drastically affect the performance. And in the case of whatever be the geometry, whether it is podded or flush or integrated intake, the duct design also plays a significant role besides just the leading edge of the intake. The design of the duct should be such that it preserves the good aerodynamics of the airframe. At the same time, it also provides reasonably good flow at the engine phase with minimal pressure loss, because pressure loss will directly affect the thrust developed by the engine, and therefore, the intake and the ducting associated with the intake must ensure that it not only preserves the good aerodynamic flow outside the intake or on the outer surface, at the same time it also gives a fairly uniform flow to the engine for proper operation of the engine, because we have already discussed about occurrence of surge and stall in an axial compressor, and these can be initiated if the incoming flow to the compressor is non-uniform. That is, if the incoming flow from the output of the intake has large non-uniformities, then those non-uniformities will enter into the compressor, and the presence of these non-uniformities may initiate the occurrence of rotating stall and maybe even surge, and that is something obviously we would as engine designers one would like to avoid. Therefore, the intake is supposed to provide or minimize the presence of these non-uniformities as the flow exits the intake and goes into the compressor. Now, the other two types of intakes I discussed, the integrated intake and the flush intake. In integrated intake, we are more concerned about the internal flow problems as compared to podded intakes, where we are concerned more of the external aerodynamics than the internal. In integrated intakes, basically we have, most likely you would have a duct which is longer and with the presence or occurrence of one or more bends. And besides this, the intake usually gets its air from the fuselage surface, which means that if there is a boundary layer developing on the fuselage, that boundary layer might feed into the intake, and therefore, the intake entry itself would have a non-uniform flow, which might get amplified by the time the flow leaves the intake. So, let me just go back to that picture I was showing. In this integrated intake, as you can see, the intake is almost adjacent to the fuselage itself. Therefore, if there is a boundary layer development on the fuselage, that would enter into the intake, and that means that the entry of the intake itself has a non-uniform flow, and therefore, as the flow proceeds or progresses through the intake, the non-uniformities may get amplified because of the presence of these curvatures, and by the time the flow exits the intake, the flow is likely to have high levels of non-uniformities. So, that is these are two limitations. One is the fact that there is a longer duct here, which means frictional losses would be larger than podded intakes. At the same time, there are possibilities that the inlet, the entry flow to the intake itself has non-uniformities. So, curvature of the duct in this case may lead to generation of secondary flows, etc., which can cause even more inflow distortion to the compressor. In the case of flush intakes, also these same problems exist as in the case of integrated intakes, but here the problems are even more compounded because of the fact that the curvature is much higher than what you see in an integrated intake. Therefore, the flow in this case takes an almost 90-degree turn, which means that the flow entering the engine is likely to be highly non-uniform. Therefore, depending upon the type of geometry of the intake that you have, the simplest being the podded intake, then we have integrated and the submerged intakes. The flow quality that leaves the intake and enters the compressor phase is likely to be significantly affected as a result of these non-uniformities. So, it is these are some of the challenges that an intake designer would have to keep in mind. Even though we are dealing with simpler components as compared to compressors or turbines, which are far more complicated by themselves, here we have simpler components, but even then the outcome of the design is likely to affect the engine substantially depending upon how the design was conceived. So, design of these intakes, even though they are subsonic, needs to keep in mind the presence or the likelihood of occurrence of these flow issues, which might substantially affect the performance of the engine. So, we were discussing about subsonic intakes in general, but some of these intake geometries may also be extended to supersonic flows, but of course, they are not the optimum type of intakes which could be used in supersonic flows. Pitot intakes are also used in supersonic flows, but they are not very commonly used because of the fact that the total pressure losses in pitot intakes when operated in supersonic flows are usually on the higher side. So, there are different types of supersonic intakes that are that have been designed and developed. So, let us take a look at what are the different types of supersonic intakes and what is it that makes supersonic intakes much more complicated than subsonic intakes. So, supersonic intakes are usually it is a fact that supersonic intakes are usually more complicated than subsonic intakes, and the design of these intakes usually involve trade-offs between efficiency, complexity, weight and cost, and that is something that the designer would have to eventually optimize and try to develop a design which will involve some sort of a trade-off between all these parameters. And supersonic intakes will usually consist of two components or two segments. One is the supersonic diffuser, where the flow is decelerated from supersonic flow to subsonic flow through a series of shocks. And then this is followed by a subsonic diffuser, where the flow is decelerated from high subsonic to subsonic flow, which is permissible for the compressor phase, usually around Mach 0.4 or 0.5. So, if the aircraft is, let us say, operating at a supersonic Mach number of, let us say, Mach 2, the supersonic diffuser decelerates the flow from Mach 2 all the way to subsonic flow, let us say around Mach 0.8, 0.9 or so. The second part of the diffuser or the intake, that is the subsonic diffuser, further decelerates the flow from high subsonic to around Mach 0.4 or 0.5, which is what is required for the operation of the compressor. So, supersonic diffuser will constitute these two components. The other complexity is that supersonic diffusers will also need to operate at subsonic speeds, because the aircraft has to take off and reach a certain altitude and Mach number before which it can accelerate to supersonic speed, which means that the aircraft has to operate at all these speeds all the way up to supersonic speeds. Therefore, the intake must ensure that the necessary mass flow rate at the required quality is supplied to the engine under all these operating conditions, which makes the design of these intakes quite a challenging task. So, let us take a look at what are the different reasons which make the operation of supersonic intakes much more complicated than subsonic intakes. Now, one of the major concerns or issues that affect the performance of supersonic intakes is the presence of shock waves, which is obviously something that is required, because deceleration from supersonic to subsonic is possible through shock waves only. So, you definitely need shock waves for deceleration, but these shock waves also cause significant loss in total pressure, and it is one of the challenges to try to minimize this total pressure loss. The other challenge is the large variation in the capture area between subsonic and supersonic flight. That is, capture area refers to the area in the free stream, the imaginary area in the free stream, which is actually delivering the required mass flow to the engine. And as the engine operates from subsonic to supersonic flight flow, the area variation of this capture area is substantial as compared to subsonic intakes, where the variation of area is not that high. Now, the other issue with these intakes is that if the engine is operating at high Mach number, then the pressure ratio that across the intake is quite high, and that will form a large fraction of the overall pressure ratio. So, the intake pressure ratio at higher Mach numbers will form a substantial part of the overall pressure ratio of the engine, which means that the thrust developed by the engine will become very sensitive to the flow through the intake itself or the performance of the intake, because thrust is a function of the overall pressure ratio, and now this overall pressure ratio has a significant amount from on account of the intake itself. So, the thrust developed will become a strong function of the intake performance. And the last important aspect of this is that efficient operation of these intakes in both subsonic and supersonic flight regime, that is obviously a very significant task. Now, let us take a look at what are the different types of supersonic intakes. You can classify supersonic intakes in different ways. One way of classifying it is axisymmetric or two dimensional. Axisymmetric intakes are usually involve the presence of a central cone or a spike, which is basically meant for fixing the shock location. Two dimensional intakes are rectangular cross sections. I have already shown you some examples of two dimensional intakes or engines which use two dimensional geometries or rectangular cross section. Other type of classification is variable or fixed. In variable geometry, if it is axisymmetric, the central cone may be movable, or if it is a rectangular type of intake, one of the walls of the intake may be adjustable depending upon the requirement. And of course, you could have a geometry which is fixed, something which is usually not a preferred type of intake. The other type of classification is depending upon the location of the shock itself. It could be either internal compression, could be external compression, or a mixed compression intake. In internal compression intakes, the shocks are located within the intake geometry itself. That is, you have shocks which are inside the intake geometry, which cause deceleration from supersonic to subsonic, and then the subsonic diffuser which decelerates from high subsonic to low subsonic. External compression intakes have shocks which are located outside the intake geometry, and mixed compression intakes have shocks, some of the shocks located outside and some of the shocks which are located inside the intake geometry. So, these are three different types of classification of intake geometries. Supersonic intakes, you could either have axisymmetric two dimensional, or fixed or variable, or internal external mixed compression. There could be intakes which have which could of course fall in all these classifications separately as well. Let us take a look at some examples of these intakes. Here we have an axisymmetric intake. This is an engine aircraft which was operational in probably the 70s. This was known as SR-71. It could operate at high supersonic Mach number of around Mach 3 or so. So, this aircraft had two engines with axisymmetric intakes. So, these are axisymmetric intakes which are supersonic, and you can see there is a center body or a spike, and this fixes the location of the shocks, and most of the time the center body or the spike location is variable, so that you can change the location of the shocks depending upon the operation itself. So, this is one example of an axisymmetric intake with a spiked center body. And this is a two-dimensional intake. This was the only civil aircraft which could cruise at supersonic Mach number, and this was Concorde, and the operation of this was abandoned a few years ago. And so, this aircraft had 4 engines, which all of them used two-dimensional intakes. What you can see here, with these are the openings of the intake. These intakes are straight, and these are rectangular in their geometry, but these are not fixed geometries, these are variable geometries, as compared to some of the, in fact most of the modern day subsonic aircraft intakes which are fixed intakes. Concorde had intakes which were variable because it had to take off at subsonic speeds and climb and reach a desired altitude before it could cruise at or accelerate to supersonic speeds. So, the intakes were required to have variable geometry. So, in this case there were movable rams, as you can see. One of the surfaces of the intake was movable, and so depending upon the operation of the intake, operation of the engine, these rams were moved, so that the engine could either operate in during takeoff, that is subsonic flow, and when it was operating in supersonic flow, these doors were closed. And so, you can see that the geometry has changed from what it was during takeoff to cruise to engine shutdown or during stopping of the engine. So, these are 3 different modes of operation of the same engine, which is possible because of the fact that the intake has some provision for changing its geometry. It is a variable geometry 2D intake. So, this is the intake of a Concorde, which was operational till a few years ago, that only supersonic transport aircraft which was operational. And you can also see that required the use of variable geometry intake, so that it could operate under different operating conditions from low subsonic to supersonic cruise and during land. So, we have just discussed the different types of intakes, the subsonic intakes and the supersonic intakes in brief in today's class. We have just had an overview of the different types of intakes, and in the next class we will probably continue this in some more types of at least the internal compression, mixed compression and external compression intakes. I shall show you some geometries which or intakes which use these geometries. We will also try to understand the performance parameters used in these different types of intakes, the subsonic and the supersonic intakes. We will also look at some of the issues related to supersonic intakes, which are known as starting of a supersonic intake. We will also try to understand what is meant by starting of a supersonic intake. So, these are some of the topics which we shall take up in for discussion in the next class. So, in the next class we will be talking about performance parameters associated with intakes, sources of losses of intake, basically the frictional losses and the shock losses, and also we will have some discussion on what is meant by starting problem in supersonic intakes, typically in the Pitot type of supersonic intakes. So, we will take up some of these topics for discussion during our next lecture.